Hello guys, in this lecture we're going to continue our discussion on the Jacobian, and we're going to look into some new characteristics of the Jacobian. So just a brief recap on, what is the Jacobian and why do we need it. So if I have a 2 degrees of freedom robot like this guy, and I have theta 1 as my first joint variable, and I have theta 2 like that. This would be the coordinate of my effector as xe, ye. With forward kinematics, I can always write, or I can always find an expression of xe with respect to theta 1 and theta 2. And I'm just going to call it f1, right? And again, with ye, I can find another relationship. And this one is theta 1 and theta 2. And probably you can guess f1 is equal to, if this guy is L1 and that guy is L2. So it would be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. So we've already described that. And we said the Jacobian is found by doing the differentiation of dxe, right? So dxe is going to be equal to the partial derivative of dxe with respect to theta 1 plus partial derivative dxe with respect to theta 2. This guy multiplies theta 1 and this guy multiplies theta 2. And dye is equal to dye d theta 1 multiplied by d theta 1 plus dye theta 2 multiplied by d theta 2. So if I have actually, if this guy were to be a 3 degrees of freedom robot, then you will just keep adding more to this guy, right? And I can rearrange this into the following. dxe d theta 1, dxe d theta 2, and here I'm going to do this multiplied by d theta 1, d theta 2. So this guy right here is my Jacobian. So I can write dx is equal to my Jacobian multiplied by d theta. Notice now that the Jacobian is a 2 by 2 matrix, right? Why is it a 2 by 2 matrix? Because it's 2, it has 2 rows, because my workspace has 2 degrees of freedom, right? So my workspace has 2 degrees of freedom, so it's 2 by 1. If I have dx, dy, if I have dz, then my workspace would be 3 by 1, right? And this number 2 here, basically, right, is dependent on, the workspace in which the robot is operating. If I have an XYZ, then it would be 3 by 1, right? If I have XYZ and then some other rotations, I'm gonna, increase that list here. And the theta basically is what? The theta is the number of degrees of freedom of the robot, right? So in this case, this is a 2 by 1, and this is, you can think of it as, number of motors, right? Or number of degrees of freedom, DOFs in the robot. And that can change, right? If that guy increases, then what happens? And this guy will increase, but that guy will never increase here, right? Because this number is actually related to this. All right. Okay. We're gonna address that in a bit as we talk about the pseudo inverse of the Jacobian, right? In the case where this guy would be a 3 by 1. Anyway, here, so if I divide by dt, what do I get? If I divide dx by dt, I'm gonna get the velocity of the robot, and this guy would be omega, right? But this guy is what? This guy is a px py is equal to j omega 1 omega 2. So the Jacobian also helped me to relate the angular velocities of the motors with the linear velocity of the end effector. So back to my robot. So it's here. What is my Vx and Vy? Vx is the velocity of the end effector in the x direction, and Vy is the velocity of the end effector in y direction. What is omega 1 and omega 2? So omega 1 is the angular velocity of the first joint, and what is omega 2 is the angular velocity of the second joint. But remember, omega 2 is the angular velocity of the second link, with respect to the first link, right? Omega 2 is nothing but, you know, how the theta 2 is changing with respect to theta time, right? If theta 2 is not changing, it doesn't mean that this guy is rotating, because remember, when we did, if we were using our DH flame, theta 2 is always is relative to the first joint, right? It could be, for example, sometimes if I provided that to you as an absolute value, then you know that would be basically different. All right. So this is what we have in that case. So there's one more relationship that I want to tell you guys is the Jacobian not only relate the Cartesian velocity of the end effector with the angular velocities of the joints, but it actually also relate the torques and the forces. And this is how it does that. So you guys know from our dynamics course what is dW, or what is a unit of work. Unit of work is what the force multiplied by distance, dx, right? And it's basically the force projected on a distance. What would be the work done by the end effector, right? Or by the robot output at the end effector, right? So it will be basically equal to, I can write that actually like that, fx fy multiplied by dx dy. You guys agree? And this work, right, so which is equal to fx dx plus fy dy, is actually, or it must be equal to the work done by the motors, right? So the work done by the motors must be equal to the work done by the end effector. So this guy is d theta 1 and d theta 2. Okay. If my force vector is actually given to me as fx and fy, then this guy is nothing but the transpose, right? So so this is the transpose of the forces, right? Multiplied by dx as a vector is equal to the transpose of the torques multiplied by the theta. Okay. Let's continue on a new page. And so I just wrote, so basically transpose of the force multiplied by dx is equal to the transpose of the torques multiplied by the theta. Now, we know that dx is equal to what? I know dx and the theta are related by the Jacobian. Then I can rewrite that as ft multiplied by j multiplied by the theta is equal to the transpose of torques multiplied by the theta. You guys agree? So then my d theta and d theta will be eliminated, and I'm going to end up with transpose of the forces multiplied by j has to be equal to the transpose of the torques. And I can do the whole thing transpose, like just to simplify it a bit. Then I'm going to do, so this ends up being what? Yeah, jt multiplied by f is equal to the torques, right? Or the torques is equal to jt multiplied by f. So if I give you the robot, right? If I give you a robot, and I'm telling you that this robot is applying, 1 Newton on this end, and it's applying 2 Newton on this end, would you be able to tell me, how much torque is being applied here, and then how much torque is being applied there? Yes, you can. You just find the Jacobian, which is a function of the link lenses and thetas, right? And then you can simply, this would be like in this case a 2 by 2 multiplied by 1 and 2, and you can tell me the torques in Newton meter. Okay, so this is another powerful relationship that we can take advantage of the Jacobian. And obviously this doesn't really incorporate the inertia, if these links are accelerating, this is just static, right? So there's no inertia, there's no IG alpha, none of that in these links, or ME or MJ, whatever. This is simply, if I have this force here, then this guy is applying this work. Okay, next step is, we mentioned sometimes you could have the Jacobian could be a 3 by 2, right? So if you have a, 3 degrees of freedom robot, 1, 2, 3, right? I have theta 1, theta 2, and theta 3, right? What would be my, so I still have only x and y, right? So I don't have a z. I have xe, ye, because it's a planar workspace. And I know xe is a function of what? Theta 1, theta 2, and theta 3, and some function ye is another function of these guys. So now, if I want to write my Jacobian, I'm going to end up with what? dxe and dye is equal to what? dxe d theta 1 to 2 theta 3, and this guy is dye d theta 1, etc. multiplied by d theta 1, d theta 2, theta 3. So how do you think you can obtain, the inverse of that, right? Remember, what we actually need is, most of the time, we need the inverse of j, right? And if you watch the previous lecture, we were using actually this guy to be able to iteratively solve the angles, where the robot should be to be able to add a particular x. So if you haven't done that, you should watch that. And if you go on MATLAB and you have a 2x2 matrix, you try to actually do the inverse you can. But if you have a 2x3 or 3x2 or any matrix that is not a square, then you will not be able to do the inverse. So this guy is what? This guy it has 2 rows by 3 مظبوط, and then this guy here is what? 3x2. So ultimately I have 2x2, but the actual Jacobian is a 2x3. Here's how you can find the inverse of that. And it's actually called pseudo inverse. It's very easy. Here's how. So if J is a 2x3, J transpose is a 3x2, right? So if this guy is a 2x3, then transpose has to be 3x2. So the whole thing of J by JT is a 2x2, which means it has an inverse. So if I take this whole thing as one matrix and then do it one more time, this has to be equal to identity matrix, right? And I have that same matrix. So this is like it's A, it's 2x2 multiplied by inverse of A has to be equal to I, right? So then all I have to do is just multiply J minus 1 on both ends. So if I actually multiply J minus 1 here and I multiply this guy by J minus 1, you see the identity will vanish. So this is J minus 1, then there you go, this is your inverse. And this is actually referred to as a pseudo inverse. So in MATLAB, if you try to do the P in PINV, it's a pseudo inverse. It will actually return this operation. And J minus 1 and J minus 1 actually cancel out. So your pseudo inverse is actually equal to this guy only, right? So the pseudo inverse is equal to that. So let me rewrite that for you. JT multiplied by what? JT minus 1, right? And regarding the pseudo inverse, it will actually be in this case, it will be a 3x2, right? It's not a square here, it's a 3x2, but you can use it to actually multiply the x, right? 3x2 and x is 2x3, so you're good. You can find a 3x1 matrix, which is this guy. Let's look into it very quickly. So if J is 2x3, then JT is a 3x2. We already said that J times JT is equal to what? A 2x2. So inverse of a 2x2 will still be a 2x2. So J hash is a 3x2, right? So 3x2. So 3x2 will multiply a 2x1. This guy is a 2x1, right? If you are rusty on linear algebra, 2 is the number of rows. So just count the number of lines, right? And then the second number is the number of columns, right? So this guy is a 3x2, right? It has 3 rows, 2 columns, 3x2, and then 3x2 will multiply 2 rows by 1, right? So if it's to the inverse, when we are doing the inverse, right? So you are always actually able to find the theta by using the pseudo inverse. And then this is how you can calculate the pseudo inverse. You don't need to program that in MATLAB, just do Pn of J, and then it will actually give you that 3x2 matrix that you actually need. Okay, guys, there is one last thing, and a few more things regarding the Jacobian to really understand what the rows and the columns of the Jacobian mean. Let's look into it one more time. So in the case of having, that 3 degrees of freedom robot, let me do it like that, with theta 1, 2, theta 3. This is my end effector with XE and YE. We said the Jacobian in this case is going to be equal to what? It's going to be equal to dxe theta 1, dxe theta 2, and dxe theta 3. And that guy here was dye theta 1. Okay, what do the different rows? So what does a column mean in Jacobian? So if you recall, so we have dx and then dy here. We have the Jacobian, and here we have d theta 1, d theta 2, and d theta 3, right? So what does the first row in the Jacobian mean? So the first row is multiplying these guys, right? The first row actually will simply tell you how dx will actually vary in response to changes in d theta 1, d theta 2, and then d theta 3, right? If the first term is 0 in the Jacobian, what happens? So if the first term is 0, so no matter how theta 1 is actually moving, dx will not move, right? If the second row is 0, if the first two entries here are 0, then dx will only vary if theta 3 vary, right? So no matter how these guys are varying, then this guy will actually not vary. Okay, so this is what is important. So each term on the Jacobian, so this term will actually tell you how dy will actually move at this particular pose of the robot. At this particular pose, how will dy move if d theta 1 has moved by a bit, right? And this guy will tell me how dy will move if theta 2, if I'm only varying the, like, you can think of it as, you're kind of, tuning this guy or whatever, right? And you are letting theta 2 to vary by a bit. So this is theta 2, and I'm letting theta 2, increase by a very small amount, right? If it increases by a very small amount, I will be able to find how the x is actually changing as a result of this amount, right? So this amount here is 1 degree, for example, right? If this is 1 degree, right? I can plug that here, and then I can find how the x will move, and then how the y will actually move. Now, regarding the column, what does the first column mean? The first column actually will tell me the contribution of theta 1 as a result of, so how does the end effector move in response to changes only in theta 1, right? So the first column, again, will tell me how dx and dy, so essentially how the velocity of the end effector, right, or how the position will actually change in the end effector as a result of moving d theta 1. The second column will tell me how the end effector move in the absolute frame or in the word frame as a result of moving theta 2. And likewise theta 3, all right? So it's very important. So the first column, what we actually call it is, we're gonna call it the JV1. So JV1 is the velocity of the end effector if you only move theta 1. So if you only move theta 1, what would be the velocity of the end effector? So you can think of this as a rigid body at this point, and you're only looking into the contribution of this guy. Well, I know that theta 1 is actually being stemmed by the 0, right? So this guy will actually be nothing but, if you remember from dynamics, it's omega cross r will give me the velocity, remember? So this guy is C0 cross position of the end effector with respect to the base frame. I can write it like that, position of the end effector, which is a 2 by 1, right, which is x and y, right, minus my initial, minus the origin of the first frame, which is 0 in this case. If you look into, so this guy will actually be equal to this, and this is called the graphical method, all right? If you do this operation, it will actually be similar to what you get here, all right? But here we're ignoring, so we're only taking the 0, we're not incorporating theta prime. It's not omega, it's only the axis about which omega is being applied. Does that make sense? So this guy is a 0 cross this guy. Now the second column of the Jacobian is going to be the contribution of this joint. So what would be the contribution of this joint? Then you're going to look into whatever axis it has. So this axis is Z1 here, remember? So this guy is going to be Z1 cross axis of actuation cross what? So it's going to be cross PE minus, remember this guy is going to be what? O1, mahike. So it's going to be PE 0 minus O1 0, right? So this will give me the second column. There is also rotational components, but in this course, we are not responsible of, as we'll see in the lecture in a bit, we also have J omega 1, which is the rotation of the end effector as a result of the first joint. So how do you actually twist the end effector? We're not really responsible for that here. Okay, so all you have to do is just understand that the first column of the Jacobian is what? Is the contribution of the first motor, right? The contribution of the first motor on the end effector. So the contribution of the first motor is basically its axis of actuation, which is Z0 cross this guy. So this will give me the direction of the velocity, right? And then ultimately, we're not really putting omega here, but we're putting only the axis of actuation of omega because ultimately we're multiplying this guy by d theta, right? If you multiply it by omega, you'll actually get the velocity. If you do d theta, you get change in the position. So what I'll do is I'm going to stop my video and I'm going to share my screen, which is the class presentation that we have. So if you look into our presentation, this is what we have, right? So this is, let's say, a 3 degrees of freedom robot. We have JV is the first column of the Jacobian will be equal to the axis of will be equal to the contribution or the velocity due to link 1, right? So velocity due to joint 1, basically, not link 1. So the velocity to joint 1 is what? So this is the axis of actuation of joint 1, which is, remember, on Z0, right? So Z0 moves link 1, and the rest of it is basically like a rigid body. Cross PE, position of the end effector with respect to the base frame. And when you are doing these cross products, you always have to be in the base frame, right? Minus a P0. So you can use the index I to be able to step into it, right? So if you look into the second joint, then JV1, right? So JV2, basically, JV2 is equal to Z1. So the second column is equal to axis of actuation of the second one, which is Z1, which does link 2, and PE minus P1. So basically, you will subtract the end effector from the first position so you can actually get the second vector. Okay. However, so this applies if the axis of actuation is rotational, right? So if it's rotational, then you're going to do the cross product. But if it's translational, then the velocity of the end effector will be, in fact, along the same direction of the axis of actuation, right? So if this guy was a prismatic joint, if it moved by a bit, then the end effector will move by the same amount, right? Why? Because we have no rotation. So the whole robot is basically translating along this axis of actuation, and then this is how you can actually get the second component, or you can get the JV of your end effector. So this is that. Okay. So here we're ignoring J omegas. Okay, so you can ignore J omegas. So we're only looking at, so JVI, if it was a rotational joint, it would be this guy. If it was a prismatic joint, it will be simply the axis of actuation. All right. So this is very important. Let's do actually a very brief example on that. So this is a 3 degrees of freedom robot, and I'm trying to build my Jacobian, right? We said, what would be, if I do my transformations, obviously, initially, so this is my T01, so we all know how to do that, right? This is, a DH here. If you plug it, you'll actually get this guy, T12, and then this is T3. What would be my JV1? JV1 is going to be, it's rotational, so therefore, it's a rotational type rope. It's rotational joints, all of them are rotational, so we're going to use this guy, right? So we'll simply apply it. So the first column in the Jacobian is going to be Z0 cross O3, or the coordinate of the end effector with respect to the base frame, minus O00, right, which is minus this point. Second one is going to be what? So I now is equal to 2, right? So it's going to be Z1, axis of actuation of the second link, cross product. So O30 will not change, minus O10. So you subtract this vector from this vector and get this vector right here, right? If you do that, what is Z00? 0 is 0, 0, 1, right? Because you have X, Y, and then Z. So all the axis of actuation are in the Z0 direction. Z01, O30 minus O10. So we know the coordinate of the end effector with respect to the base frame, which is O30. We have it from, well, if you do the multiplication, you will actually see it very quickly. It's going to be this, minus 0, which is the origin of the first one. So this is my first column of my Jacobian. JV2 is this guy, minus 010, you're going to end up with this guy. It's pretty straightforward. And then this is how you can actually obtain your Jacobian in the graphical method. So this is a graphical method of obtaining the Jacobian. We said we're ignoring j omegas here. All right. J omega basically is simply like the twist, right, by how much you are actually rotating the end effector, in the base frame. And, it's not very intuitive and pretty much don't mean much. If you were to actually look into it in more detail, so, remember we have dx, dy, dz, so you can think of, you could also have, rotation along x, rotation along y, and rotation along z. And here you will actually get your rotational. And you get the 1, you get the 2, you get the 3. Okay, so this is our j omega, and then it's not included in our course, but I'll tell you, it basically simply means by how much you are rotating about the x. So as a result of varying these guys, how much you are rotating in the x direction, right? How much the whole robot is basically rotating in the x direction. This is not really included in our case, and you don't need to be concerned with it. You just need to be concerned with the linear components of the Jacobian, which is the first thing. All right. And by the way, regarding omega here, right? So why do we have 1, 1, 1? Is, no matter if you move theta 1 or theta 2 or theta 3, right? The robot is rotating about the z, right? So it will basically, you will basically kind of compound the change in the angles. So if Q1 changed by a bit, Q2 changed by a bit, and then Q3 changed by a bit, we know my rotation will only be applied along the z direction. Again, you don't need to, worry about that. This is not going to be included. You're only responsible for finding JVs. So this is another example. We have rotational. We can begin by obtaining our homogeneous transformation, T01, T12, T23, right? We can obtain T01, T02, and then T03. So we are able to obtain the position of the origins of these frames with respect to the base frame. I can write, P0 in the base frame, P1 in the base frame, and then P2 in the base frame, P3 in the base frame. And I will basically simply, and then I would need my Z0, my axis of actuation. So Z0, I know it's going to be along the Z0 axis, my case 0, 0, 1. So this is my first joint. The second one is along what? So the second one is basically you're looking at Z1 in frame 0, right? So Z1 in frame 0, it's actually a bit rotated, right? Because as soon as the first one begins to move, your axis of actuation is going to rotate, right? How can you also get it? If you obtain the homogeneous transformation, if you obtain H01, Z1b is what? Is the third column, right? And the H01 transformation. Okay, so this is Z1b. Let me do it here on to clarify that. So I can put my H01, right? I can write my H01. H01 is going to be equal to what? X10, Y10, Z10, right? So this is Z10 that you are going to need here, right? So this is my Z10, okay? Z20, again, you'll look into H20, and then you can use H20 to be able to pull this guy. So once you really understand how to really move between frames and then look at a homogeneous transformation to obtain a particular vector, you will be really, really, in a very good shape in terms of understanding the material of this course. So, this is a big part of this course, and being able to understand, all the interrelationships between all these homogeneous transformations, and then how to obtain this rotation matrix, how to obtain the coordinate of a point, how to actually create like a virtual frame, and then use the virtual frame to be able to capture its origin using the transformations, I think is something that is very powerful. So here now, just applying these equations that we have, and we can basically obtain the Jacobian using the graphical method. So that is pretty much it regarding the Jacobians. This lecture is just another what we just discussed earlier, right? We can use the pseudo inverse, how the pseudo inverse is calculated. So this is just another. You can read through this guy as we just explained that this is Jacobian pseudo inverse, etc. So I think we're good with this lecture. Any questions, guys, on these materials? Just please feel free to email me, and I'll be very happy to set up any Zoom call or to help you to understand the material.